Hello, we are Team 19 working for the Shape Corporation based out of Grand Haven, Michigan. If you are unfamiliar with Shape, they are mainly a roll-forming manufacturer who produce parts for car bumpers. Roll forming is the process of taking a coil of sheet metal and running it through a series of rollers that slowly bend it into its final shape, and then each piece is cut to length at the end of the line. The goal of our project is to measure the key specifications of the sheet metal before it is fed into the mill. Currently, Shape measures the quality of its sheet metals by measuring the final product in a fixture. By this point, the mill is filled with the sheet metal, and if it does not meet specifications, the line needs to be adjusted or the roll needs to be replaced. We will be able to detect if the sheet metal is out of spec before it's fed into the line and can stop the mill to allow for these changes to be made. For the key specifications, we will be measuring the thickness, width, and the crown or the bending of the sheet. The standard for reading measurements is to have an accuracy of 10 times the tolerance. This leaves us with an accuracy for the width, thickness, and crown of 0.025 millimeters, 0.016 millimeters, and 0.016 millimeters respectively. The other dimension that is read is the length of the coil, which needs to have an accuracy of 0.0142 millimeters. Each line uses various widths of steel, which can range from a foot to 2 feet wide. The device needed to be able to accommodate for any situation. Our solution would be able to work for not only our designated line, but also for other lines if it were to be moved or copied for another station. The best concluded solution was to use a combination of contact and non-contact sensors to record the dimensions of the sheet steel as it passes through the device. Our device does not require the line to be halted while measurements are being taken. The measuring device needed to have a slim profile as it would operate in a tight 5-inch wide space, and it needed to read material 6 feet off the ground. The device would also need to consider the effects of vibration from nearby machines while the coil is fed through the assembly line. Lastly, the team was informed that due to the harsh environment we are operating in, plus also taking into consideration the tolerancing needed, aluminum extrusion would not be the best option. Taking this into consideration and all the parameters of the project, it was determined that a steel frame made of tube steel would be the best option. The frame would be a perfect base to weld the features to the structure while also enduring the harsh environment. In order to record various widths of steel, there needed to be mechanical features that could adjust the sensor locations while allowing the sheet steel to be fed through the device. Adjustable aluminum plates, termed C-plates, were the solution to flexible reading positions and being lightweight. The C-plates would be physically removed in a linear fashion by using rails and runner blocks with ball bearings. The center aluminum plates would remain stationary since they are designed to only record data in the middle of the sheet steel. The encoder to measure the length was also mounted to these center plates. A steel plate with a square cutout for the coil to feed through would be the foundation for the adjustable C-plates and the center mounting blocks that hold the sensors. Steel brackets were welded to the tube steel frame to hold this main plate in position. This was to ensure that the main frame would not warp during the welding process. The C-plates would be bolted in place with locating holes to fix them in the proper width of steel being fed. For safety, we had poke yoke sensors that were mounted to the frame so that the device can verify the C-plates are in the correct position before any sheet metal is fed into the mill.
Before designing the mechanical fixture, the sensors used to obtain the required measurements were selected. To measure the width, a non-contact type of sensor had to be used. This is because the sharp edge of the thin steel sheet would have damaged any contact sensor probe. The LS7030 sensor was chosen to measure the width. Two of these sensors are used, one at each edge of the steel. This sensor has an emitter that shines green light towards a receiver. The receiver can detect how much light has been blocked by the sheet and calculate how far the sheet protrudes into the sensing area. The two measurements from these sensors are added to the known distance between the sensors to give us the actual width of the steel. The LS7030 has an accuracy of 0.001 millimeters, which meets the accuracy requirement we set for our sensors. To measure the thickness, non-contact sensors were preferred, but did not fit within the budget. The GT2A32 LVDT contact sensors were chosen instead. These sensors have replaceable metal roller tips and are able to be retracted to prevent interference when a new sheet of steel is fed through the device. The LVDT works by having a center core that is attached to the probe transfer a magnetic field from one set of internal windings to another, the amount transferred being based on the position of the core. In our application, the LVDTs are mounted with their contacts touching each other when fully extended. In this configuration, the LVDTs can be calibrated to a zero position and extended against the steel sheet. And when extended against the steel sheet, the sum of the LVDT measurements will be the actual thickness of the steel. To measure the length of the steel, a rotary encoder that is used on other roll form lines at shape was supplied by the sponsor. The length measurement from the encoder will be used to tell the PLC when to record data from the sensors, as the measurements will be coded for every inch of steel. The LRTB5000 laser distance sensor was chosen to measure the distance from the C-plates to the main steel frame. Having a sensor measure this distance is critical because if the C-plates are fashioned into the wrong position, the measurements will be incorrect, the system could be damaged, and employees could be harmed. The purpose of this sensor is to verify that the C-plates are in the correct position for the given width of steel being run in the mill, and if they are not in the correct position, to prevent the mill from running. The electronics that control the device are contained within two enclosures. The main enclosure houses most of the electrical components, and the HMI enclosure houses the HMI and other human interface devices, such as an e-stop, safety reset button, and stack light. The main enclosure is powered by a standard 120 volt outlet, which feeds a 24 volt 5 amp power supply. The power supply is located in the top left corner of the cabinet to isolate the incoming 120 volt cable from the electrically sensitive sensor wires. To the right of the power supply is the PLC, which is the computer that runs the device. To the right of the PLC is the safety relay. This relay is connected to the e-stop on the HMI panel. When the e-stop is pressed, the safety relay cuts power to its contacts. This removes power from the pneumatic valve, retracting the LVDTs, and also breaks the circuit to the main line's safety relay network, stopping the entire roll forming line. This ensures our system is fully integrated into the existing manufacturing process as safe as possible. To reset the safety relay, the e-stop must be reset, and the safety reset button must be pushed. When the safety relay is reset, the safety reset button lights up green, indicating that power has been restored. To the right of the safety relay is the point I/O and the LVDT amplifiers. The point I/O is responsible for the sending and receiving of discrete and analog signals. Some of these signals include the length measurement from the encoder and the output signal to the pneumatic valve, to name a few. The LVDT amplifiers power and receive data from the LVDTs. A communication module sends this data to the PLC via Profinet, so there is no quantization error from the point I/O's ADC. The bottom row of DIN rail includes the 4-pole circuit breaker to protect against short circuits, an Ethernet switch to connect the PLC to the existing roll forming lines PLC, and terminal strips for power distribution and wire organization.
The week following project day, we are going to take the device to shape to implement our device into their line. Because the device is so heavy, is going to take some strategic planning in order to put the device into the correct location without harming anybody and without damaging other components of the line. Our plan is to use a forklift, lifting straps, and multiple people to guide the device into the enclosed space where it will be permanently located. Our device will be secured to the ground using 12 concrete anchors to prevent tipping since it is almost 7 feet tall. Validation testing has shown that our device works correctly and it accurately measures the dimensions of the sheet to the required specifications. We hope that Shape finds our device useful, and we look forward to saving them time and money with our device.